this lecture we are going to look at the problem of deadlock-free packet switching. So, as you may be aware that the most of the networks that we have today, they are packet switching networks. In other words, that the messages are broken down into packets and then the packets are routed from source to destination. Now, because the intermediate nodes may receive packets with different destinations, they will have to store those packets in their local buffers and then forward it to the next node according to the routing table. So, that means that if I have a particular node and then when that node receives a packet from some neighbor W with a destination V, then it will store it in some buffer. It will store it in some buffer, and then from that buffer it is then going to look up the routing table for destination V, and then suppose the destination V can be reached along the neighbor Q, then it has to forward it to Q. So, again the packet will be forwarded from this buffer to some buffer at Q, right. So, actually the packets are routed from one buffer, from the buffer in one node to another buffer in another node, okay, and this is how they are stored and forwarded until they reach their destination. Now, because these buffers are of finite size, there is a possibility of a deadlock. Okay. We will first see an example of such a deadlock. So, suppose we have these 4 nodes S, T, U and V, and S has all of these nodes has a buffer size of 5, okay, and let us suppose that node S is sending 5 packets to V through T, okay. So, just a moment, yeah, suppose S has these 5 packets to be sent to V, and the next node for S in its routing table is T. So, it will forward all those 5 packets to T. Okay. Let us say at the same time V has 5 packets which has to be sent to S. Okay. So, V looks up its routing table and finds that the next node on the path to S is U. So, it forwards all the 5 packets to U. Now, see that T has 5 packets which must be forwarded to U, and U has 5 packets which must be forwarded to T, but none of them have any empty buffer, right. So, there is no way that a packet from here can be copied into some buffer here, because this is also, all of these are occupied. So, this is a deadlock situation. Now, T cannot forward any packet to U, U cannot forward any packet to T. And if you have understood this, you will realize that this is a simple deadlock involving only 2 nodes, but in general there can be a complex deadlock involving many nodes, and the deadlock situation will be that it will involve a set of nodes such that none of these nodes can forward any of their packets to their next node. Okay, so, that kind of deadlock situation is possible. So, instead of dropping packets when the deadlock happens, we will see that there are several distributed strategies by which you can prevent deadlocks. Okay. So, we will have to do buffer management. We have to decide when we are going to allow the forwarding of a packet such that the overall system does not deadlock. Okay. So, this is the problem that we are going to study, that we have understood what is a store and forward deadlock, where every node or a subset of the nodes are deadlocked in such a way that none of them can forward their packets to their next nodes, and we will try to see what kind of buffer management strategy can guarantee that such a deadlock does not happen. And what is the buffer management strategy going to do? It is going to tell us that when there is a packet with a certain destination V, when are we going to accept the packet, when are we going to forward the packet, and to which buffer in the next node are we going to forward the packet. Okay. So, these are the things that will be decided by the strategy, and then we will prove that there are strategies which are deadlock free. Okay. That is the topic that we are going to study in this lecture. So, first let us look at the model. The network is a graph G having V vertices, V is the set of vertices, E is the set of edges. Okay, so, the network is a graph. Let us say that each node has B buffers. Okay. B is some constant, each node has B number of buffers. There are three types of moves. Remember that we always look at distributed computation as a set of moves. Okay. Something happens from the environment and the node reacts to that. Okay. So, here there are three types of moves. The first type is generation of a packet. A node U creates a new packet P and places it in an empty buffer in U. Node U is the source of P. This is how new packets are generated. Okay. Forwarding. A packet P is forwarded from a node U to an empty buffer in the next node W on its route. Now, for a packet U, for a packet which is at node U and has destination V, the identity of the next node is not determined by the buffer management strategy. The identity of the next node is determined by the routing algorithm. Okay. So, we must not confuse that when we are talking about buffer management and deadlock free buffer management, we are not dictating the path through which the packet should traverse. The path through which the packet is going to be routed is determined by the routing algorithm. Okay. All that the buffer management strategy decides is on the next node on the path, which buffer are we going to use to store the forwarded packet. Okay. That is in the jurisdiction of the buffer management algorithm. Okay. So, a packet P is forwarded from a node U to an empty buffer in the next node W on its route. So, the next node W is determined by the routing algorithm, and the empty buffer to which it has to be moved is determined by the buffer management strategy. And finally, the consumption. A packet P occupying a buffer in its destination node is removed from the buffer. Okay. So, when it has reached the destination, when the packet is stored in a buffer in the destination node for that packet, the packet is consumed by the higher layers of the network stack. Okay. Is this clear? The model is clear? Yes or no? The packet, these are the requirements of a packet switching controller. First requirement is the consumption of a packet at its destination is always allowed. Okay. So, whenever the packet is reaching its destination, we will assume that it is going to be consumed. Okay. So, there is nothing that prevents its consumption when it is in the destination. The generation of a packet in a node where all buffers are empty is always allowed. So, if there is a node where all buffers are empty, then every packet switching controller must allow the generation of a packet in that node. Okay. If all of the buffers are not empty, then different controllers may choose whether it will allow generation or not allow generation. Okay. The controller uses only local information. That is, whether a packet can be accepted in a node U depends only on information known to you or contained in the packet. Alright. This is the third requirement. So, we do not want to send messages to other nodes asking what is the status of your buffer, nothing like that. every node will decide whether or not to accept a packet based on only local information and whatever information is there in the packet. Okay. And what information does the packet have? It can have information like what is the destination, okay, size of the packet and things like that. Clear? Now, there are various solutions that are there for this problem, and we are going to look at broadly two types of solutions. The first type is called structured solutions, okay, where we are going to define a thing called a buffer graph, and under this class of solutions we are going to look at three different types of algorithms, and then we will look at unstructured solutions possibly in the next lecture, where we will look at two different types of algorithms. Okay. We define a buffer graph. So, intuitively a buffer graph is a virtual graph which is physically not present, but it is a virtual graph defined over the buffers in the network. So, remember that every node by our assumption has b number of buffers. Okay. Now, a buffer graph will be defined as a graph where the vertices are the buffers in the different nodes, and there are some hypothetical edges, namely ones through which we will route packets. Okay. Now, let us see the definition first. The buffer graph is a directed graph BG. We will use BG for buffer graph on the buffers of the network such that firstly BG is acyclic, so it contains no directed cycle. BC is an edge of BG if B and C are buffers in the same node or buffers in two nodes connected by a channel in G. Okay. And for each path pi belonging to P, okay, what is P? P is the collection of all paths followed by the packets. This collection is determined by the routing algorithm. So, if you look at the network, then packets from any destination U to any destination V is routed through certain paths, right. Those paths are determined by the routing algorithm. Let us look at the collection of all such paths. All such paths through which packets can possibly be routed. Okay. That set of paths is P. Okay. So, it is a subset of the paths in the graph representing the network. Now, let us be very careful about this. We are talking about two graphs here. One graph is the graph which represents the network, that is physically the set of nodes and the set of channels in the network. Okay. P is a subset of paths of that graph. Which subset of paths? Those paths which are used by the routing algorithm to route packets from some node U to some node V. Okay. Now, for the buffer graph,
P will contain all the nodes of the network.
it should, because it should be possible to route packets from any node to any node, right. So, it is quite expected that P will cover all the nodes of the network, but it may not cover all the paths of the network. For example, it may be the case that whenever I route packets from A to C, I route them from A through B to C, not from A through D to C, right. So, the path ADC may not be there, right. So, that kind of thing is possible. So, but what we must make sure is the buffer graph for every path P that a routing algorithm must use, there must be a corresponding path in the buffer graph. So, for each path pi belonging to P, there exists a path in BG whose image is pi. Now, why do we have this requirement? Because you see, we are going to use the buffer graph to store and forward the packets. Okay. What is the buffer graph? Buffer graph is a network of buffers. Okay. Now, let me give you a picture. Suppose we have 4 nodes. Okay. Let us say I have 3 buffers. Right. Now, suppose this could be a buffer graph, for example, that I have okay, and the other one could be something like this. Now, see, in this buffer graph, this is the buffer graph. Okay, there is no cycle. There is no cycle in this buffer graph. Okay, and the graph is defined over the buffers of the in the network. All right, and suppose the actual network is this. Suppose the actual network is a ring. What we must guarantee is that for every routing path here, okay, there must be a corresponding path in the buffer graph. Okay. Is it clear what we are meaning by the buffer graph? Channel between, not between 2 buffers, channel between 2 nodes. See, BC is an edge of BG if BNC are buffers in the same node, or BNC are buffers in 2 nodes connected by a channel in G. Yeah, so what we mean here is, see, here between U and V, there is no channel in the network. So, you will not have any edge from a buffer in U to a buffer in V. Okay. There is no edge from a buffer in U to a buffer in V, neither from a buffer in V to a buffer in U. Why? Because there is no physical channel between U and V. Okay. Now, let us understand why we are constructing this buffer graph. We are constructing this buffer graph because we want to route packets from buffers in U to buffers in W, buffers in U to buffers in X. Remember that the routing of the packets means storing and forwarding the packets from one buffer to another buffer, buffer in one node to a buffer in another node. That is how the packet actually physically travels from buffer to buffer, right. What are the constraints? You cannot copy a packet in one node in a buffer in U directly to a buffer in V. You cannot do that. Why? Because there is no physical channel between U and V, right. And that is one thing that defines that you can only have edges between U and W and U and X and X and V and V and W because there are physical channels there, right. The second thing is that if there is a routing path like say UWV, suppose there is a routing path UWV that packets from U to V are routed through W by the routing algorithm, then there has to be a corresponding path in the buffer graph if we have to store and forward the packets along the edges of the buffer graph, right. So, the corresponding path in this case for UVW could be this, from this buffer to this buffer and from this buffer to this buffer. Okay. There can be extra paths because all we want to make sure is that the set of paths P is covered by the set of paths in the buffer graph, alright. But the buffer graph can have additional paths because that will help in reducing the total number of buffers in certain cases. These are all virtual. These are all virtual.
If the buffers are not empty, then you will not have such a path.
No. There is nothing to do with emptiness of buffers here. The buffer graph is a graph through which we are going to route, actually store and forward the packets. We are going to store and forward the packets along the edges of the buffer graph. Okay, that is our intent. Now, we have to make sure that for every routing path there is a corresponding path in the buffer graph, period. Okay. Why we can have additional paths is because you can actually, multiple routing paths can share some of the paths in the buffer graph. Okay. For example, let us suppose take this example. Okay. Suppose the routing algorithm, whenever it routes packets from U to V, it either uses this path or uses this path, right. So, there are 4 possible paths from U to V, this, and then there is this, and then there is this one, right. Let us say that it only uses these 2 paths P1 and P2 for routing packets from U to V. Okay. Now, suppose we want to implement this because this is a directed graph. So, we suppose we want to implement it with one buffer in every node. Okay. One buffer in every node. So, then what is the buffer graph going to look like? It is going to look like this. Now, you can see that for packets that are going from U to V, we can route it through these buffers, no problem with that. But the buffer graph has also these additional paths, this one and this one, right. Now, there is nothing wrong in it, there is no harm in these additional paths being there. Those paths are there because in the buffer graph we just used one buffer. So, we could not distinguish between the paths that are there in P and these additional paths, right. In order to do that, we would have to use 2 buffers here. If you just wanted to confine yourself to only these path P1 and P2, then we would have to use something like this. in this buffer graph only P1 and P2 is supported, only the two paths P1 and P2 is supported. In this buffer graph you cannot have this path, right. But then what happened, we had to use two buffers here to distinguish between this path and this path. Did you get it? So that is why it is possible that the buffer graph will have more number of paths than P. So there is nothing bad about it. All we have to guarantee is for every routing path there is a corresponding path in the buffer graph. Buffer graph is not unique. So different strategies will use different buffer graphs. But we will first study some generic properties about these buffer graphs and what kind of properties guarantee that there will not be any deadlock. Now we will further define two terms. One is called a suitable buffer and the other is called a guaranteed path. Let P be a packet in node U with destination V. A buffer B in U is suitable for P if there is a path in the buffer graph from B to a buffer C in V whose image is a path that P can follow in G. Now let us understand what do we mean by this. We are saying that a buffer B in U is suitable for the packet P. What is the packet P? It is a packet in node U with destination V. Okay. We are trying to figure out where can we store this packet. We are trying to find out a suitable buffer where we will store the packet. Which packet? The packet which has arrived at node U with destination V. So we are saying that a buffer B is suitable for P if there is a path in the buffer graph from B to a buffer C in V, the destination V, whose image is a path that P can follow in G. Okay. What does that mean? See, for a packet with destination V, the routing algorithm will determine what is the path that it will follow from U to V. There has to be a corresponding path in the buffer graph, right. Now there can be multiple paths corresponding to that in the buffer graph. So any one of those buffers which are in those paths is a suitable buffer. Okay. One such path in BG will be designated as the guaranteed path. Okay, and NB-PB denotes the next buffer on the guaranteed path. So our algorithm will tell us that which is the next buffer on the guaranteed path. Meaning what? I have a packet with destination V. I am node U. I have a packet with destination V. I have put it in some buffer in my buffer. I have put it somewhere in my buffer, and now I consult my routing table and find which is the next node in the routing path. Let us say W is the next node in the routing path. Now I want to determine that which is the buffer in W to which this packet will be forwarded. Okay. Now that buffer should be a buffer on the guaranteed path on the buffer graph. Okay. And I will call that buffer in W to which this packet is forwarded as the next buffer or NB-PB. Okay. So for each newly generated packet P in U, there exists a designated suitable buffer FBP in U. Okay. and for forwarding every packet there will be a designated NBPB to which it will be forwarded. NB stands for next buffer, FB stands for first buffer. Okay. Let us look at what we mean by a buffer graph controller. So, buffer graph controller is a controller which is going to decide how packets are routed through the buffer graph. Okay. It has to satisfy the following requirements. The generation of a packet P in U is allowed if the buffer FBP is free. So, when I generate the packet in U, I will check whether FBP is free. If it is free, then the generation will be allowed. If it is not free, then the generation of the packet will be suspended. If the packet is generated, it is placed in the buffer FBP. The forwarding of a packet P from a buffer in U to a buffer in W is allowed if NBPB, which is a buffer in W, is free. So, node U will be able to forward a packet P to node W if NBPB in W is free. Yes. So, if it is free, then W will accept the packet. Remember that every packet, when it is forwarded from one node to another, has to be acknowledged, right. So, if the next node, that is W, cannot accept the packet, then it will drop it. So, you will know that I will have to send it again. Okay. So, the packet is not accepted by W unless NBPB is free. Is it clear? If the forwarding takes place, then P is placed in NBPB. Right. Now, what we will prove here is the buffer graph controller that we have defined like this is a deadlock free controller. Okay. So, what have we, let me summarize what we have done so far. We have defined what is a buffer graph. We have defined that the buffer graph is an acyclic graph. It contains no directed cycle. We have said that there can be an edge in the buffer graph if the two buffers are in the same node or if they are in two nodes connected by a channel. And the third property that we have said is for every routing path in the network, there is a corresponding path in the buffer graph. Okay, this was the definition of the buffer graph. Then we defined a buffer graph controller which does the following thing, that it allows the generation of a packet if a designated first buffer is free. We have not said how we decide which is the first buffer, we have not said that yet, but all we have said is that the generation of packet P in U is allowed if the designated first buffer is free, and then for every packet in every buffer with every destination, there is a designated next buffer. Okay. And we forward the packet to the next buffer only when the next buffer is free. Alright. Now, based on this information, we will be able to show that the buffer graph controller is a deadlock free packet switching controller. Right. Now, remember that corresponding to every path in the routing determined by the routing algorithm, there is a corresponding path in the buffer graph. Right. Now, so the existence of paths is not the problem. All we need to show is that the packets do not deadlock in any configuration, that deadlock is not possible. Okay. To prove that, we define what is called a term called a buffer class. Okay. What is a buffer class? The buffer class of B is the length of the longest path in BG that ends in B. Okay. So, you take any buffer B, okay, this is some buffer B. Now, in the buffer graph there are many paths that end in B, there can be multiple paths that end in B, right. Out of these paths, the buffer class of B is the length of the longest path that ends in B, right. Okay. This longest path is well defined because the graph is acyclic. The buffer graph BG is an acyclic graph, alright. So, there are no cycles, there are no directed cycles in the graph, it is a directed graph and there are no cycles in the graph. Okay. So, there is a longest path that ends in B and that is the buffer class of B. Now, consider a buffer. Okay. So, let us say that all the buffers in the network, we can classify them based on buffer class, okay, by this definition. So, buffer class 1, buffer class 2, buffer class 3, buffer class 4 and so on, alright. Let R be the highest buffer class. Okay. Now, take a buffer Z whose buffer class is R. Z is a buffer whose buffer class is R. What does that mean? That the longest buffer, the longest path in BG that ends in Z has a length of R, right. Now, this Z cannot have any outgoing edges. Why? Because if there was another outgoing edge to some buffer Q, then Q will have a higher buffer class than this, right, but then R is the highest buffer class. So, this one can never have any outgoing edges, right. So, what do we conclude? We conclude that packets which are there in Z, they can only be consumed, they cannot be forwarded anymore, right. Now, see, because the buffer graph is acyclic, there will always be nodes directed and acyclic. So, there will always be nodes which have out degree 0, and for those packets in those nodes, they will always be consumed because they cannot be forwarded anymore. There is no outgoing edges from there, they can always be consumed, right. Now, we want to show, we will use induction on R. We will use induction on R to show that for all buffer classes, deadlock cannot happen. So, all we have shown is that the packets which belong to the highest buffer class cannot be deadlocked because they can be consumed. Okay. Now, how are we going to show that for a buffer class R which is less than R, we have to show for this buffer class also there cannot be any deadlock packet, right. So, to prove this, we will use induction on R, and the induction hypothesis will be, what will be the induction hypothesis? That for each R dash with R less than R dash less than equal to R, okay, no buffer of buffer class R dash contains okay, this is our induction hypothesis. R dash, this the induction hypothesis, what are we trying to prove? We prove that for R equal to, for R is the buffer, is a given buffer class. So, if R is R, then nodes which have buffer class R equal to R do not contain any deadlock packet. That is what we showed here, that for all buffers having the highest buffer class, they cannot have deadlock packets, right. Now, we are using the induction hypothesis saying that for all R dash which is between R, small r and capital R, for all of them the result holds, that is no buffer of class R dash contains a deadlock packet. Using this hypothesis, we will show that then no buffer of class R can contain a deadlock packet. If for all R dash which is greater than R, no deadlock packets can be there, then for buffer class R also there cannot be a deadlock packet. Okay. So, that is how we will use the induction. Is it clear? Now, see, if you look at any buffer Z which belongs to the class buffer class R, it can contain two types of packets. So, this is in node U. We are talking about a buffer in node U, the name of the buffer is Z and the buffer class of this buffer is R. Okay. Now, what kind of packets can it have? It can, suppose it contains a packet with destination U, then it will be consumed. If it is not of destination U, then it will have a designated next buffer which is NB for the packet P, NB PU in some node W, right. What is the buffer class of this? The buffer class of this is R plus 1. By the induction hypothesis, this does not contain a deadlock packet. So, if this does not contain a deadlock packet, it will eventually become free, because that packet will eventually be either consumed or forwarded or whatever, it is not deadlocked. And then when this one becomes free, then P can move here. So, neither is this deadlocked. Okay. Right. Now, we have not proved a great thing. All we did prove is that if you have the buffers arranged in an acyclic graph, then in the acyclic graph you can never have a cyclic weight of buffers. That is all that we have proved. So, if you look at all the paths, then the paths which end with the largest length, for them there is no out degree, right. There are nodes which have no out degree. So, their packets will be consumed. Then the nodes which are just before that, then their packets will also not be deadlocked. Why? Because if we look at any node which is not deadlocked, then all the nodes which have to route packets to this, neither are these ones deadlocked, because this one will eventually be consumed and then these packets can come in and then, okay. So, that is what we did. We looked at the induction hypothesis and said that, okay, for all paths, for all those which have buffer class of R dash which is less than my current R, so for all of these there are no deadlocked packets. Then we conclude that then these also cannot be deadlocked, because they either consume the packets or forward it to some buffer in the next buffer class, right. Okay. Now, the main issue here is, therefore, what is the main issue here? How will the algorithms differ from each other? So, all we have said is we need to virtually construct this buffer graph, and then packets will be forwarded along the edges of the buffer graph. Question is, how do we construct the buffer graph? Because we are going to use only local information. So, there is no central authority which will create the buffer graph and then communicate that to all the nodes. There is no such thing. So, the buffer graph is virtually constructed in a distributed fashion, right. Algorithms will differ in terms of how this buffer graph is constructed, right. And then we also, what is the optimization criteria? Optimization criteria is how many buffers do we need. Can we do it with 2 buffers, 3 buffers, 5 buffers? How does the number of buffers change with the size of the network, by the topology of the network, and so on? Okay. So that's why we will now look at different types of schemes for buffer graph controllers. The first one is a very simple scheme. It's called the destination scheme. So what we do is we use n buffers in each node. Okay, we use n buffers in each node u with a buffer buv for each possible destination v. It is assumed that the routing algorithm forwards all packets with destination v via a directed tree TV routed towards v. Okay. The buffer graph is defined by Bg equal to Be, where Bu V1, Bu V2 belongs to E if V1 equal to V2 and UW is an edge of TV1. Let me give you an example because that is the easiest way to understand this. Suppose I have a network just excuse me. Suppose this is the network. Okay. Now let us look at how packets with destination 4 are routed. All right. So packets for destination 4, they may be routed like this, that this is, now see, for packets with destination 4, they cannot be routed along any cyclic path. Routing always is done through an acyclic. So let us say that it is something like this, that routed like right. So this is what? This is a tree rooted at 4. All right. Okay. Let us look at how packets are routed to 2. So for packets that have to be routed to 2, we will have a tree rooted at 2. Okay. For packets with destination 1, it could be and for packets with destination 3, it could be now see what are these? These are 4 trees. For each destination, we have a tree along which the packets are routed to that destination, right. Now node 1 is going to have these buffers. So B11, B12, B13, B14. These are the 4 buffers that node 1 has. Okay. Node 2 has this buffer, this buffer, this and this. So every node has n buffers, right. In other words, what is happening here is that you look upon this graph as a collection of 4 graphs in 4 different planes. Okay. So, for nodes with destination 1, we use this tree. For nodes with destination 2, we use this tree. For nodes with destination 3, we use this tree, right. Now, the buffers, so I have in every node I have these 4 buffers, right. Now, this plane consisting of the top buffers is used for the tree with destination 1. This plane consisting of the second buffers is the one which is used for routing packets to 2. Is that clear? Now, obviously, there is no cycle in this graph because each plane is a tree and there is no edge between the from one plane to the other. Okay. So, it is a acyclic graph, all right. So, there is by virtue of what we have seen before, there is a deadlock free controller which uses this. In the next class, we will see another buffer graph controller which uses a slightly different scheme and uses fewer buffers than n. Okay. And then we will see at some more generic solutions of this. Okay. Clear so far?